So today we are going to develop the idea of what is limit superior and limit inferior of a real bounded sequence. Now these two notions could be developed irrespective of the fact that the real sequence is bounded or not, but as of right now we will stick to the fact that the given sequence is bounded, because we are not working in the extended real number system. Our domain is restricted to the real domain system, which does not include the infinities, the positive infinity and negative infinity, as part of the real number system, which is uh, essentially the extended real number system. So our primary objective is to show the equivalence between the definition given in Tao's analysis 1 and Bartle's definition of what is a limsup and what is a liminf, because these two definitions might seem different while comparing. I mean, if you juxtapose these two definitions, then these might seem different, but they are exactly the same. Now, later on, we will develop the equivalence. As of right now, I will take inspiration from Tao's lecture notes. So, let an index from 1, starting from 1 to infinity, is a real bounded sequence. Then, to define what is limit superior of this sequence, I will take the help of an auxiliary sequence, or in other words, I will construct another sequence, an plus, whose general term is given by this expression. It is defined to be supremum of this set. What this essentially conveys is that this is supremum of the set an plus 1, an plus 2, and so on. I mean, you just discard the first n minus 1 elements of the given sequence, this sequence, and then take the supremum of the the resulting set, which was that is what is essentially n plus. Now there are two key observations, and I will represent them using claims. Now my first claim is indeed, this is claim 1, that this sequence an plus is a monotonically decreasing sequence. Now this is now to prove, this is proof of claim 1. Now to use this, I'm going to use a lemma that you must be familiar with. I mean, suppose A and B are two sets where A is a subset of B, then supremum of A will be less than equal to supremum of B. So this is the rudimentary idea that I am going to use to prove this statement. Now A1 plus is nothing but supremum of an starting from 1, which is supremum of A1, A2, and so on, A3, and so on, which is basically the supremum of this set. Now this exists. This is well defined because by the completeness of real numbers, as we know that this is a real bounded sequence, hence supremum of that set must exist, and so we denote the supremum of that set by this thing A1 plus. Now A2 plus is nothing but supremum of this set supremum of this set just by discarding the first element. Now observe that an starting from 2 to infinity is a proper subset of an starting from 1, because this is nothing but an starting from 2 to infinite union a1. So this is a subset of this one, or this is a superset of this one. So we must have supremum of an starting from 2 to infinite less than equal to supremum of an starting from 1 to infinite, or a2 plus is less than a1 plus, right? So now inductively you could show that similarly you could show that a3 plus would be less than a2 plus, and a4 plus would be less than a3 plus. Then using induction you could show that ak plus 1 plus would be less than ak plus for all k belonging to n. What this essentially conveys is that an plus is a monotonically decreasing sequence. So this was our first claim. Now this result is useless unless the sequence is bounded below. So I mean magically that's how it works. This sequence is also not even magically, mathematically, of course, because the sequence is bounded below. That is exactly my second claim. An plus is bounded below. Now, since our original sequence was a bounded sequence, hence we must have mod of an less than equal to some positive real number capital M for all n belonging to n. And if you just remove the mod, you could say that an is greater than equal to minus m for all n belonging to n, or minus m is a lower bound for the given sequence. Now you could easily show that an plus would always be greater than equal to minus m. How? For any arbitrary n, capital M, n plus is nothing but supremum of this set. So as we know that supremum of a given set is always going to be greater than equal to any element of that set, and since an belongs to this set, so by definition of supremum of a set, this must be greater than equal to an. And since minus m was a lower bound of the original sequence, a capital N must be greater than minus m. And since capital N was arbitrary, therefore an plus is greater than equal to minus m for all n belonging to natural numbers. So now we have a lower bound and a monotonically decreasing sequence. And hence, by courtesy of monotone convergence theorem, it must have a limit, and that limit is in fact infimum of the sequence. So limsup of the sequence, let us denote it by capital L plus, is nothing but limit of this sequence. So this is the definition of limit superior of a real bounded sequence. Now on a similar basis, exactly if you just mirror the definitions in context of infimums, obviously, I mean for an plus you define the corresponding term will be an minus, which will be infimum of this set index from capital N to infinity, and you could show that an minus is a monotonically increasing sequence and an minus is bounded above. So the limit exists, and this would be equal to supremum of that sequence. Yeah, supremum of that sequence, which is defined to be liminf of the original sequence, or I can denote it just by L minus.